Sitaram, can you just see if I'm live?
I'm joining on your phone.
Okay, looks like we are live. So welcome everyone to this. This one is a special one because this is a project that has a lot of impact and is also very important, especially in the times that we are living in. So I have Anool and Vaibhav from the Makers Asylum, which is one of the most well-known makerspace in this part of the world, and they have been working on a very interesting project, which is the M19O2 oxygen concentrator. So I'm going to let them tell you more about that. But before that, Anul and Weber, if you could just quickly introduce yourself for folks who haven't met you before.
Okay. What about you? Want to do it?
Guys.
Okay, hi guys. This is Weber Chabra. I'm co-founder at Makers Asylum and chief learning officer. I'm a mechanical engineer and love making stuff since pretty much as long as I remember. Anul, why don't you go ahead?
Hi guys. I am Anool, engineer without a degree is what I like to call myself. I've been co-founder at Asylum since it started. I love making things. I also am part of the Hackaday crew where I write blog posts. Uh, and I generally like to make and build things a lot. I like to teach
Is
a lot,
Anul?
and my interests are essentially open source tools like for those you use for CAD and circuit design and so on. So that's me. And then we have Gorbachev.
Gobajav, if you could unmute yourself and just give a quick intro.
I do that. So hi, so I'm Gorbachev. Same story, like love making stuff. I have, I mean, basically that's what it is. I mean, love making stuff. I was in network architect before. I have now quit that job. We'll be focusing completely like building stuff. Start with this is going to be the oxygen concentrator. From there on, we'll move forward to some interesting projects which is in the pipeline. Right now, helping Anul with whatever we are
You
doing
should
here.
drop a few words of that exciting projects that you're talking
Exciting
about.
projects.
I'm more excited about that for you.
Okay, so we are building like a jet engine right now. That's the first stage. So we're going to be building a jetpack. Basically, put multiple of them together to build a jetpack. If all of that goes well, we might have a big size drone, like a VTOL drone. That's the long term plan. I have 1 year to myself for this entire thing. If things don't work out, I'll have to go back to do what I was doing before. So that's it for now. Yeah.
Well, we wish you succeed on that because I'm really waiting to see that VTOL jet engine fly. All right, Anuj, up to you.
Okay, I think Anuj was having some trouble with the power supply.
No, I'm back. I'm back. I'm back.
Oh,
I'm
okay,
back.
awesome, great.
Sorry about that. But yeah, thanks guys for the introduction. So I'll quickly share the project page, which is on GitHub as well as Makers Asylum's website. So if you check this, so this is Makers Asylum's GitHub, and this is the M19O2 page. So like I mentioned in the description and on the Telegram group and on Twitter as well, this is an open hardware project, right? So if you have all the materials, you could actually build your own. And Anul and Vaibhav and Gobacha, they have included a lot of nice documentation. We were just taking a look at that before we started this. But Anul or Vaibhav, if you want to take it from here, we'd love to hear about how you came up with the idea, like the motivation behind it, and like then we could go on to the technical stuff, which I'm pretty sure a lot of people are excited about.
Okay, so Vaibhav, if you can walk through the N19 and how PSA system works, then after that I can take over to show how the machine works.
Sure. So a little background about the M19 initiatives. You can hear me?
Yeah, loud and clear.
Okay. Okay, a little background about the M-19 initiative. Last year, when COVID hit, few of us, Anool, myself, Richa, and a few of us quarantined at Makers Asylum at the beginning, and started to see what we can do, because it was obviously better to be around the lab and all the tools than to go back home and quarantine at home. So that's when we started with the making the face shields. So you can see them actually behind me, the board, all the prototypes over there. So we went through about 21 design iterations, and very quickly were able to scale from 0 to 1 million shields by creating a distributed network of labs all across India and sharing designs openly and working on them in an open way. That became quite exciting. Then we also worked on a few other projects like the M-19 respirator, which is an active respirator. I have one here with me right now. So air blows directly inside the hood of the doctor, especially for high risk environments. Usually something like this costs about 2.5 lakh rupees. By 3M, we were able to bring down the cost to about 10 to 15,000 rupees, along with AIMS Hospital in Delhi. Then we were working on rebreather masks for senior citizens. And this year, with the huge oxygen shortage, we decided to look at the oxygen concentrators. And initially, we started with a few prototypes of open source oxygen concentrators, but now we've moved quite a bit forward by trying out multiple prototypes. Anool has been leading the journey for the engineering side, and will be showing you how the oxygen concentrator works. But to just give a brief aspect, the oxygen concentrators are based on a PSA-based system, which is a pressure
Vaibhav,
swing.
interrupt you for a minute. Yeah, Anuj, if you can show this diagram,
Yeah.
and then Vaibhav can follow up with his explanation. Perfect. Go ahead, Vaibhav.
Okay, so the oxygen concentrators are based on a PSA, a pressure swing absorption technique, which means that, like you can see over here, there are two sort of stages to it. One is that when one of the sieves is open. So basically, there are two sieves at the oxygen concentrator with zeolite packed inside it. One of them starts filling up with nitrogen and uh, releases oxygen from the outlet, while the other one right now is depressurizing and is removing the nitrogen into the environment. And then this thing sort of swings, and now the other sieve starts pumping out oxygen, while the first one is now removing the nitrogen. So in a very simple way, that's how you're able to sort of pressurize and depressurize your sieves while producing oxygen in a concentrated manner using just regular atmospheric air. Anything else, Anul, you'd like to add?
Yeah, so at the heart of the process is pretty old, and the patent has also expired by now. So there's nothing new in terms of how it works. The trick is in a synthetic mineral called as a zeolite. Zeolites of a particular type, which are known as molecular sieves. And a molecular sieve is pretty much similar to a regular mechanical sieve. It can allow certain things to pass while blocking other things. So in the case of the zeolite used in the oxygen generator, the mineral will absorb, or rather, it won't allow nitrogen to pass through. It blocks the passage of nitrogen uh, molecules through the two towers that you see here. But the oxygen atoms or molecules are free to pass through. So when you pass pressurized air through the chamber, all of the nitrogen gets trapped in the sieve, while the oxygen passes through to the outlet. And once the first tower is kind of saturated with nitrogen, we kind of flip the process and start pressurizing the second one. And at this point, the previous tower starts releasing all of the nitrogen that it has captured back into atmosphere. So essentially, we're taking air with 79% nitrogen, 20% or 21% oxygen, passing it through this molecular sieve, which blocks all of the nitrogen, and the output will end up with about 90-95% of oxygen purity. And the flow or the output depends on the size of your system in terms of how much pressure you have, what's the size of your towers, and so on. But uh, it's a pretty straightforward process. There's a Wikipedia page on it that describes it quite well, which is where this diagram is also taken from. So check that out. So that's pretty much essentially how the process works. Like I said, the key element to this is the zeolite mineral. That's important, or the heart of the whole process.
Okay, so
But beyond that, technically or technologically, there's really nothing new in it. It's a very old process. It's been used in industry for quite a long time.
right, so a quick question. So there are three things that you need. One, regular air.
So I'm wondering if the
Can you
others
hear
have
me?
dropped out.
Vaibhav, can you hear me?
Yes, I can hear you.
So I think Anul can't hear us. Okay.
Okay, Anool is joining back. You can ask the question though. I'll try and answer for him.
Yeah. No, so mine was a pretty straightforward question. So you need three things here, right? So one, you need electricity, one, you need regular air, and you need zeolite.
Yes, but you need to pressurize that regular air, so you need a high power, high flow rate compressor, which is
No.
also oil.
I meant in terms of consumables, like things that we consume during this
Yeah.
thing. Yeah.
Well, the zeolite is not a consumable.
Oh, okay.
Once the sleeves are packed, the zeolite should run for about 2 years straight.
Okay, so then technically there's just two consumables, which is air and electricity, which are
Right.
two things that are pretty easily available.
Correct, because the pressure swing absorption method basically regenerates the zeolite every 10 seconds. So you're not really eating up the zeolite, you're just sort of regenerating the zeolite. It's absorbing nitrogen and then throwing it out, absorbing
Okay.
nitrogen, throwing it out. So the zeolites end up lasting for about a year or two.
That's actually pretty awesome, because then all you need is just air and electricity. So this could be working in like a completely remote setup.
Correct.
Yeah, true.
So then there's no logistics as such involved, which is a major issue with O2 cylinders, right?
Yes and no. I mean, it comes with their own set of things to take care of. But yeah, much better than having relying on cylinders for sure.
Yeah.
Because
Okay.
pretty much oxygen on demand. You have it when you
Yeah,
want it.
exactly. Yeah, exactly. Okay.
Well,
Okay. And
oxygen cylinders are able to provide a much higher flow rate compared to the concentrators.
right.
So this concentrator tries to address one of the problems by providing a higher flow rate of 15 lpm, but
Okay.
an oxygen cylinder can still provide higher flow rate than that. I think it goes up to about 25 plus lpm.
Right.
Is that correct,
And
Anool?
Yeah, but at that point, patients are really serious. Oh,
right.
Yes,
I mean,
Right.
concentrator might not really help. You really need the cylinder by then.
Right.
correct.
Okay. And like in terms of percentages, are the cylinder and oxygen concentrator similar? About so you guys are
Yeah,
doing
pretty
plus
much.
90, right?
Pretty much. Oxygen cylinders can be more than 99% purity.
Okay.
But with the pressure swing adsorption, you cannot get more than 95% theoretically. Because
Okay.
your air is 79% nitrogen, 21%
Right.
oxygen. The balance is argon, mostly argon and some carbon dioxide. So the
Right.
PSA system only removes the nitrogen. So all of the oxygen along with some of the argon goes out. Uh,
Got
which is why you get about 95% oxygen max and about 4 or 5% of argon and trace amounts of carbon dioxide in the output of your oxygen concentrator.
Got it. Okay. Okay. That's good to know. Okay. What do you guys want to show us next?
Okay,
Because
I
I'm
guess
seeing the data sheet and the assembly manual, and both are very interesting.
Probably you can post links and folks can check it out.
Yeah, I'll do that.
But maybe I can now give you a walkthrough of the machine. Yes.
Yeah. Yes. Let me just.
So this is here what I have here in front of me. That's the front part of the machine. That's the side, and that's the back. And it all starts with this compressor. That's where we suck in air from the atmosphere. We pump it through these two heads, and the output goes to these two copper cooling coils because the compressed air is quite hot. So, and it also contains a lot of humidity. So we pass it through the copper coil, which helps to uh, reduce temperature a bit and also to condense some of the water, not all of it. Uh, the output of the copper coils then uh, goes to a device. Let me show it to you. Here in the front, this thing which is known as a moisture separator. So it's got an inlet and an outlet, and you have humid air coming in, and all of the moisture gets trapped and collects here at the bottom, and at the output you get dry air. So with this, you can see right now I'm at 90% humidity in ambient air. Uh,
Right.
this device helps us bringing down to about less than 50 or so, sometimes better than that, 40. But that's good enough for a system like this.
Okay.
So once you have that air that's kind of dry, we send it to a solenoid valve. Not sure if you can see the red light here.
Yeah.
And that solenoid valve then controls how the air goes into these two towers. So these are the two sieves, the sieve A and sieve B. And at any given time in the process, while one is being pressurized, the second one is depressurizing back to atmosphere. So both are working in that fashion. So once this starts getting pressurized, the air that fills in here, all of the nitrogen gets trapped in this zeolite that's filled in here. But the oxygen kind of flows out of the outlet at the top. So that's where the outlet is. And here at the bottom is where the inlet is. This one. So the air goes in, this traps all the nitrogen, and the oxygen keeps going out. While that is happening, the second one has some of the oxygen coming out from here, pushing back into this sieve. So that lets you uh, bring the nitrogen back out over here and back into the atmosphere. So that's an important part of the process. Uh, Use the outlet oxygen to push nitrogen back into the atmosphere. And then, of course, that process keeps repeating every between 5 to 10 seconds. Uh, the output of these two sieve or towers is combined over here, and it goes into this third chamber, which is basically an empty tank. That's more of a reservoir. It's called a surge tank. Uh, that sort of smooths out the pulsating output of these two uh, sieves. And let me show you the other side. The output from the surge tank is controlled using this flow regulator, and from there you can see it come here into this HEPA filter, and from the HEPA filter it goes here into this flow indicator, and from there this is the outlet of the machine that gets you the oxygen. That's why you put some water to kind of humidify the dry oxygen. So essentially that's the whole part of the machine. We got some lots of cooling fans here. We got cooling fans here to keep things cool. Uh, we have a pressure switch. So in case of overpressure in the system, the compressor is cut off. Uh, this one here is the oxygen sensor that's measuring the output of the machine. And yeah, we have some electronics here. It's a regular Arduino Nano and a shield that has relays that control the timing cycles and so on. And all of that running off this 24-volt power supply. And yeah, that's about it. So that's the front user interface. That's an emergency push button. The power switch, the fuse, the display right now that's showing ambient temperature, humidity, oxygen, and if the compressor is on or off. Uh-oh. It's going to get noisy because I'm going to switch it on, but just wanted to show you the electrical rating. You can see that without the compressor, this thing is drawing about approximately 33 watts at 240 volts. That's about 0.3 amps. So this part of the system can easily be powered by maybe a battery or a renewable, source like a solar, for example. But once you turn on the compressor, that's a lot of power. This is about 1,200 watts. Let me put on the compressor.
So you're measuring both the input and the output, O2 and humidity.
So once it crosses 80, this turns blue. Once it crosses 90, it turns green. It takes about a minute or two for it to stabilize.
Anool, what's the feature for those cool googly eyes?
Sorry, I couldn't hear you. Come again.
What
just
do
asking.
those eyes do? Are
What
those
do
Sorry?
those
eyes
eyes
there
do?
for surveillance?
Okay, come again. There's still too much noise. What's the?
Yeah, yeah, nothing. We were just curious about what the eyes do. The googly
Okay.
eyes.
The googly eyes are, well, a nice touch by Richard, but I think I really like them here. Uh, since it's an open source project, we don't have to be too serious about it.
So there's a quick question in the chat, Anul.
Yeah.
Sitaram's asking, how low do you have to cool the air? So when you said that you are passing it through the copper pipes,
Yeah.
uh, like how cool does it get? So
Okay.
assuming
So,
it's at room temperature or something, it
okay.
gets hot
So
because of the compressor.
the output of the compressor is anywhere between 70 to 90 degrees, the
Okay,
air temperature. After the cooling coil, it's down at least about 30 degrees.
okay,
And once it goes through this, it comes down some more. So by the time it's entering over here, it's somewhere in the ballpark figure about 40 degrees or so, I'd say.
okay. And then finally, when it's available to the patient, would it be at room temperature?
Yeah, that's pretty much cool because once it
Okay,
goes through the tower, it sort of cools down.
right, got it. Okay,
Also,
so one more
in real
interesting
world
thing,
conditions, this goes through water, so that also cools down the oxygen quite a lot.
right, got it. So one part of this whole process is removing the water, the humidity, and then also adding it at the end, right? Initially,
Yeah,
you
because you can't breathe the dry oxygen. Apparently, it's not safe. In fact, if you, which is why one of the reasons why you can't have more than 15 LPM is because oxygen can also be quite poisonous to the human body.
Okay, I didn't know
So
that.
it's,
Okay.
yeah, I mean, it's an oxidizer, right? It kind of reacts with everything. So excess oxygen isn't really good for you,
Okay. Okay. So
which is
so you
why
have to
when
have the just right amount.
yeah, so when doctors are treating COVID patients with a really serious case, there is a specific protocol on what liters per minute they can give and for how long before they reduce it and turn it back on and so on. It's quite complicated.
Right. Okay.
So of course I've just kind of opened up all the side panels so you get a glimpse of what's inside. But these are the different side panels that have the acoustic foam on it for sound insulation, because that's one of the important requirements for a medical device to have less than I think 50 dB or so. I'm not sure of the exact number, but of course it needs to be as wide as possible.
Right. Are you hitting those numbers yet? Or do you
We
need more
haven't yet tried
information?
because I really don't have access to a sound meter right now. But I think we did some tests
Okay.
in Goa. What were the numbers we were getting, Weber?
We were about 65 decibels,
Yeah,
Okay. Getting
okay.
there.
which is not bad at all because that's like a human voice or
Yeah.
Right.
like music.
Right.
Also,
So
we have to balance between two things. One is we want to ventilate and cool the compressor, and at the same time we want to isolate its sound because the major sound comes from the compressor. So those two requirements make it a bit difficult to kind of balance the sound insulation part.
Got it.
Yeah.
Okay. So you said that right now it's like 33 watts, and when you turn it on, it's close to 1,000 watts, right?
Yeah, let me push it on again. That's about 6 amperes.
Got it. So it could technically run on your standard 6 ampere socket that everyone has at
Or
home, right?
yeah,
Or
but
does
of
it
course
require the 16 amp?
we insist it works off a 16 amp for safety reasons.
Got it. Right.
Yeah.
Yeah. Good to have a margin of safety there.
Yeah. I mean, with the compressor off, this is, I mean, because of the switch mode power supply, which is most of the power that is throwing at the four fans, the power factor is like about 0.5, I think. But once the compressor turns on, it's about 0.7, 0.8. So not too bad.
Got it. Got it.
And you can see here the moisture, water dripping out from the pipe.
Right.
That's from just a
So
few seconds of running right now. That's the pipe
uh,
that goes to the separator over here.
right. Could you just connect that to the OTU or like O2 humidifier?
Uh, we haven't tried. At the moment, it just goes out of a drain at the back of the panel. This, this thing you see here at the bottom.
Yeah. Got it. Got it. Got it.
And we hope the end user then sort of connects it to some kind of a drain or whatever.
Got it.
But yeah,
Nice.
it's kind of still
But
dripping
I
water.
think it's not a very strong flow, right? I think it's dripping there.
Yeah, it drips, but it's I mean the quantity is quite substantial.
Okay.
Because as you can see, yes, I mean we are at 90% over here.
Right. Yeah. Okay.
So
So it's directly proportional to your humidity. So
yeah, yeah.
that's the amount of work it's going to have to do.
So in fact, a lot of our time was trying to figure out different ways of reducing humidity in air. So I think we spent almost a month trying different methods, including refrigeration. Even Gorbachev here has tried different ways of putting through chilling the air, so you can condense the water and extract it out and so on. And one of the nice things we tried at Goa was actually the same as this pressure swing adsorption system for removing moisture from air instead of removing nitrogen from air. So it works in the exact same fashion. Uses a slightly different zeolite, but using that you can bring humidity down from about 90-95 down to about single digits, like 9% or 3%, between 5 to 9%. RH.
Nice.
Uh,
Okay.
but eventually, end of the day, we figured out that it doesn't really have to be that low. If you hit about 40%, 35%, you're good enough to run the machine. So with
I
that,
have the I have the refrigerator on my screen.
oh yeah,
Yeah,
let's see that.
I'm just sharing that. Wow.
So air comes in from here. This is just a sort of refrigerator radiator sort of a thing, and this is the output that goes into the compressor. That's the compressor heat exchanger. So that's what's cooling basically this guy, and all the water basically collects right here before going into the machine. Uh,
Wow.
while I'm on it, that's the
Yeah,
second
show
unit.
the work.
That's the second unit being work in progress over here in Goa, giving the same output, giving the same results, just waiting on a few last parts to put it and close this machine now. But pretty much ready.
How many units
This
do
is
you
the
guys have in
Frankenstein.
total now?
Frankenstein, the first model that we'd made using uh, based on the OxyKit design, and then these are some other oxygen concentrators. The one coming in from China uh, that we've been studying and also fixing more. Yeah, this is the final one right here.
You had a question,
Nice.
Anuj?
Yeah, so how many units do you have to go through? How many prototypes did you guys have to go through before you guys got to the one that is, looking polished? Because looks like
Vaibhav.
you guys went through like a half a dozen or so prototypes.
Well, close
Primarily,
enough. We made four prototypes. This is version 4.
so
Okay.
four primary, like four versions of it, but in the middle, I think we tried a lot of maybe like 100 different
Oh, yeah.
configurations in each prototype. So multiple smaller versions, but primarily four versions, four major prototypes.
Nice. So you started off with the OxyKit version, and then you started doing more changes to that, and that's how you ended up with the M1902. Is that how it worked?
Yeah, exactly right. So I mean, we of course built the Oxygen to figure out how it works and what is required.
Right.
But at that point, we pretty much knew that it's something that can't be used in hospitals because made out of wood and PVC, and
Right.
both of these are materials that a hospital really won't accept, especially as a final device. And it had a lot of other shortcomings. It didn't have moisture separation, for example. It didn't have an online oxygen monitoring, so you really didn't know how much oxygen it was making and so on. So we kind of got back to the drawing board and built this whole thing from scratch, pretty much.
Nice.
Yeah, this is
Although
some remains.
while we were building it, I mean, this took us about 2 months. We started off sometime around the beginning of May, and we were doing this in Goa. So Goa, we have several special challenges. So there one is, of course, power keeps going and coming at a whim. Sometimes it goes off for a really long time. Then we had a cyclone that knocked everything out for a week. We were without light or anything else for a week. So in fact, we even ended up purchasing a genset to make things work. And ordering anything in Goa, like if you want, an electrical part or an electronic part, could take anywhere from a week to 2 weeks to arrive. So uh, scrambling and designing and making things while thinking ahead and ordering what we required was really a balancing act that we kind of somehow
So
pulled off. I'm not sure how.
yeah, so looks like you've technically field tested this device already while
Pretty
prototyping.
much. I mean, it
Yeah.
survived a long car journey from Goa to Bombay, so I can say with confidence that it's undergone vibration testing and passed with flying
Yeah.
colors.
Yeah,
So that's one
definitely.
of
I
the
mean, if
tests
it
that
survived
we,
that journey, yeah, you don't
yeah.
need to do any more vibration testing
So
on
that's
that.
one of the tests that the lab will do to check its performance.
Got it. So what's next in this journey? I mean, you've gone
So
through.
next is, I mean, once the the covers are on. This is pretty much a product that can be put on the field. But we still need some external validation from a lab to make sure that it works. So there's two parts to it. One is a functional performance test to tell us what's the percentage oxygen it's making at how much LPM, what's the power it's drawing, and so on. So, what are the electrical parameters, what's the noise it's emitting, and so on. That is fairly easy, and I think we should be able to get that done quickly now. But beyond that is certifying this to the standard, the international standard for oxygen concentrators. That's 80601 2 69. And
Okay.
frankly, that's a pretty long journey because there are a lot of tests that are involved in certifying medical devices from the aspect of safety. So once we submit it to a lab, we may have certain, let's say, list of non-compliances there. They'll tell us this thing doesn't work or this thing fails or you have to change a certain part and so on. And it's a process that goes back and forth while we try to clear out those non-compliances. And if we are successful at that stage, we will have a device that is certified to 80601, which will be, I think, quite a challenging task. If we can actually pull it off, I'll be pretty elated.
Nice. Yeah, I was wondering about that because I mean, if it's a medical device, there's going to be a pretty long list of requirements that it has to check, like tick. So
Absolutely. So medical devices are covered under IEC standard, that's 60601. That document is actually a whole series of documents. I think maybe 25, 30, I'm not too sure. The main document is about 700 pages long.
wow.
And then there is the specific standards for oxygen concentrators themselves, which is another document that we have to worry about. So, yeah, it's a very, very involved process. It's not something that you can kind of walk through. You have to do a lot of hard work to get that done. Which is why we are
Wow.
not sure if we want to do that because we may or may not have the bandwidth to do it at this point in time because of cost, time, or other implications. But certainly the functional testing, if we can get through, that at least proves that the machine works as expected in terms of its operational requirements.
Right. That makes sense. And then, are you planning on? So I'm not sure how this works, but are you planning on making kits? Because
Uh,
that would.
that's a good idea. Maybe we really haven't given it a lot of thought, but yes, there will be some things that might be easier for others if they are kind of available off the shelf.
Right. Exactly.
Certainly, the main thing is, of course, the assembly of the seal. I think that's the most critical part of the whole system.
Right.
So maybe we can look at making that simpler for others, and once that is there, then after that it's a question of putting essentially your compressor, your cooling system, your electronics, put it all together, wire it up pneumatically and electrically, and you're done. So should not be too difficult.
Oh,
Your
so
thoughts?
yeah. What your thoughts on this? Like, do you think like this could be a kit?
So initially and since the beginning, Anool and all of us, we envisioned this to be an educational project. To be able to sort of share as much as knowledge as possible on these critical devices, and at the same time use this as a learning sort of project. Number one, to learn more about oxygen concentrators, obviously, and what we can do. But at the same time, what we've been building is a platform through the M-19 collective and the M-19 initiative, where now we have over 600 people a part of the collective that have been openly sharing designs and making stuff. 125 labs have joined the collective. And
Wow.
the agenda is that if all of us work together and share, we can really create pretty much anything, right? And that's one
Yeah.
primary advantage to this. Uh, and what's also something that we're working with is that this year, the University of Cambridge has also joined forces with us. They've been funding this project, and they have been
Oh.
working with us on quality assuring since and quality checks. So basically, Cambridge University has a department for distributed manufacturing, And Professor Mukesh, who's been leading that, has him and his team has been extensively doing research with us on the oxygen concentrators and helping us out, while also working with us on ways in which we could take the oxygen concentrator and build QA QC processes for other labs and other makerspaces. So they're able to basically copy the M-19 oxygen concentrator and replicate it and still have the same sort of certification and standards as ours if they follow a specific sort of pattern that is what the guys at Cambridge are building. They're building a sort of an app that will basically guide them through step by step on how to build these things pretty much any part of the world.
That would
Yeah,
be actually pretty interesting, and it sounds like a challenge as well, because it's like you need to build a machine in a distributed manner, and it has to perform in a standard way,
exactly.
because given that it's like a medical
Just to
machine
give
and
you
Yes.
everything.
a background, for example, here's Gorbachev's prototype one. Uh, it's again pretty much just a test bed. Okay, there's really not much to it in terms of a product. But after this, Gorba, you mind showing us your design as it is now? You mind showing us your design as it is now? The SolidWorks. Is it okay? Okay, so let's see what Gorbachev is working on. I mean, he's making the same thing, but putting his own, thoughts on what he wants it to be like. So that's the system that is going to look like, and he's basing it off the work that we have done. It doesn't have to be exactly what we have done, but if he follows the QAQC practices that we lay down and does his own thing, this is a product that he can go to market.
Nice.
That's the kind of plan. And then we have similar labs, like for example, we have diverse labs in Chennai who are working on their version of it and so on. So uh,
So you already
people don't
have
have to be
people
married to
making.
this. They don't have to be married to this. They can make their own,
Yeah.
version of it.
So this reminds me of like the 3D printer projects where people are taking designs and mixing and prototyping them and making their own in certain ways. So this feels a lot like the early days of
Exactly.
rap to me.
Yeah. But there are certain challenges. For example, certain things are critical in this. You need to
Yeah,
have a
of course.
seal with a certain, quality and parts and so on. Same thing with the compressor. So as long as the other people follow those instructions and change the non-critical things or parts, oh, that's great. For example, Gorbachev is working on a much better way of cooling the compressed air and removing moisture. That doesn't involve making these coils, because making these coils by hand is quite a task. It takes quite a while to make one. So if that can be replaced with a different device that doesn't require so much manual work, that will make things better.
Yeah, maybe we can look to for water cooled PCs as an
Exactly.
example. Yeah,
Yeah.
that might be actually interesting.
Yeah.
There's another question in the chat, like how hard was it to get the zeolite?
Pretty hard.
Because pretty hard.
So the story with zeolite is there are quite a few manufacturers around the world. There's some in France. There's a few in Russia. There's of course Honeywell. These are all big names. There's Arkema in France. There's a couple in few in India as well. But primarily the biggest source has been from China. Fortunately or unfortunately, they have better pricing for the same product. So that makes a big difference for us. So at
Right,
this point, we are depending on them for the zeolite itself.
right.
I heard that there were a couple of teams in India that were working on local development of zeolite specifically for oxygen concentration. There was at least
Okay.
one team at IIT Madras, I think, that was working on it, but not sure what the status of those projects are, or if it will even become commercial sooner or later. I don't know.
Right. Because yeah, I mean, I've been looking at this design, and there are definitely a lot of complicated and complex assemblies here. But if there's some chemical things that we have to get it manufactured, especially, then that might actually be the bottleneck for more people trying this out.
Exactly.
Got it. But yeah, it's good to see that you already have people forking the work that you have done, and trying out
Absolutely.
different things. Yeah, that's
Uh,
very good to know,
so the
because that
design
means
is
the
pretty much well detailed. We have created lots of documentation for it. We have data sheets. We have a user manual of how to use it. We also have an assembly manual that shows you how to put it all together. So there's a ton of documentation that is out there. Just today, we also applied for the OSHA Open Source Hardware Association certification. So hopefully that should come through quickly as well, because this one is pretty well documented in terms of its open source requirements.
Yeah, I've been looking at the GitHub repo, and I see a bunch of documents there. I've also posted a link to that in the chat right now.
Yeah.
But yeah, I mean, I see an instruction manual, an assembly manual, and a data sheet there. So that's pretty
Most of
well
the action is
documented.
in the engineering folder, and there's a deep, it's a deep folder containing a lot of subfolders and stuff like that. But a lot of things happening there within the CAD folder, for example.
Yeah, I see. I see. There's quite a lot of
Because
things here.
while making this, we had to do a lot of things. For example, for the seals to function properly, they need to be very well compacted or compressed. That's
Okay.
a practical requirement. Otherwise, when you push air from the bottom, it kind of just flows out without getting trapped in the zeolite. So the zeolite
Right.
has to be well compacted. So there needs to be some kind of a vibratory jig that can shake the seal while we are filling the zeolite in it, and make sure that the powder is really well compacted. So we have to make a shaking or a shaker jig or a vibratory jig to make this. Uh, Also, in order to maintain compression, the top of the seal has a very strong spring over here that keeps the whole column compressed. And because of the spring, fixing the top cover is not really easy. So we have to build a jig to kind of compress the top cap while we can put the screws. Uh, so a lot of these jigs are there in the engineering folder as well, and so on. So there were a lot of side projects we had to do to make this.
So you are not just making the concentrator itself, but also the things that help you manufacture the
Yeah,
concentrator.
pretty much. There was a separate team that worked on the unified circuit board layout for it. Uh, I was too busy doing other things, so I didn't have the bandwidth to help them out. But they made a good job using a controller that uses ESP32 and exposes all of the GPIOs, the I2C and SPI and so on. Uses a nice display. Uses a better Bosch sensor for temperature, humidity, and altitude. So because that's another thing that affects the performance of the machine is if you take it at higher altitudes, because of the air density, the performance suffers obviously.
Okay, so sea level is like the best place to use an
Yeah,
oxygen concentrator.
yeah. I think it's like a 10% drop for every. I forget. I think I mentioned it in the data sheet, but yeah, there is a performance drop in terms of elevation gain.
Okay, that's interesting. Uh, and so one more question that I have is like, how can someone support this? I remember there was a crowdfunding initiative that you guys had on Kettle. Is that still going on? Are you guys looking to,
Weber,
still,
that's Weber's domain.
like, if someone wants to back this, how do they help you guys out?
Is Weber around?
I think so.
So anyway, yeah, I think the keto campaign still goes on, and
Okay.
one of the things that we are using those funds is to support other groups that are making the concentrators.
Yeah,
So
because now you got
funds
a
are
nice
not,
community going on.
yeah, yeah, they're not just for us to do the research, but the other places like Chennai or Bangalore or Bombay who are working on this, they are also be receiving the funding to for doing the research on this. So it's it's more of a community, let's say, crowdfunding campaign. So But yeah, I mean, if you don't want to, support monetarily, there's other ways to get involved in the project. We have a lot of Telegram groups. There's of course a main group, but then there are subgroups for things like engineering or documentation or certification and so on. And you can join in there, and sort of, if you have skills that we can uh, be useful to us, well, I'm happy to have you on board.
Got it.
As
Yeah.
Weber
So
mentioned, we have a huge community already. There's more than 400-500 people lined up who are working on different things and ways.
yeah,
So
I'm just
the
going to
thing,
post a link
while
to
it may
the.
seem, as of now that the oxygen problem is gone, uh, that could be a yes and a no. We really don't know unless the third wave hits us and we figure out what happens if it's affecting kids or not. Uh, but for us, this is more of a long game. It's not just about oxygen concentrators. It's about one, how do you build a community of people who can collectively brainstorm, so do collective engineering in terms of research, and do distributed manufacturing locally. And these two things are really possible only with a community. So the M-19 initiative more towards that long-term goal. Like it's oxygen concentrators today, but we can easily scale this to something else tomorrow, for example.
Very
Yeah,
true.
and I think that's quite important because one thing that we have realized in the last 2 years or 18 months is that uh, supply chains are getting disrupted at an insane level.
Talk to me about Chipocalypse.
Yeah, so like we've seen that in our work as well. Like things that should be easily available are not being easily available. So having the ability to manufacture something as important as a concentrator locally and in distributed manner is like a no-brainer. You have like more people have to get involved in this. Cool. So I have
Also,
posted.
coming back to an earlier question on testing, it was a bit of a chicken and egg in the situation because there are no manufacturers of auto concentrators in India, and hence none of the test labs actually set up a facility to test auto concentrators. So, bit of an issue, which is also one of the reasons why we are facing some trouble. But we have identified a lab that does testing of medical devices, so they would be able to mostly do most of the tests that we wish to do. But yeah, these are things that go more against, from a, let's say, um, infrastructure development side for the government to, kind of
Right,
get back together in terms of setting up facilities or, encouraging local manufacturing and so on. So uh,
right.
let's see how things go on that front.
Yeah. I think like the ability to test and certify certain kind of equipment, be it medical or auto industry or water industry. This has to come from the government. I think there's no other way for that
Yeah.
to really happen. Uh,
To start with, the
and
standards are pretty expensive, so it's not easy. You can't just go out and buy them. You have to
yeah, exactly.
kind
Yeah.
of.
Okay, I have a very open-ended question, but like, and this is open for both of you.
Yeah,
Which was the toughest part? Because
Which
this
was the
seems like a
toughest.
multi-month project,
Yeah.
and you had to build a lot of things yourself and learn quite a lot. Because I'm looking at the research folder and there's a
Uh,
bunch of things.
Not too sure. I mean, 2 months in Goa was a big challenge. I think that was the biggest challenge because mainly uh, you can only do things when you have stuff available. So, sourcing parts, uh, the failure of infrastructure in Goa, when that was a natural calamity. So there was nothing we could do about, cyclone coming and
Right.
breaking down everything. We had about 1 feet of water in the Maker's Asylum for about 1 or 2 days. So we were busy kind of
Wow.
getting rid of that and, fixing leaking roofs. And so that was not something we had signed up for making concentrators, but we had to do it because there was no other option. So
Right.
these are the things. And then we had no connectivity. There was no phones working. Uh, So the challenges were more on that side, getting hold of things, getting hold of facilities, uh, looking around and hunting for certification, looking around and hunting for the parts that we needed. Those were the really bigger challenges. I mean, we knew how to make it. If we had the parts, this is, like I've said in one of my earlier videos, this isn't rocket science. But
Right.
uh, making it needs a lot of things to come together at the same time, and that was a bit difficult to achieve over 2 months. Even so, I'd say two
Yeah.
months is a fairly good turnaround time for a project of this size and
Yeah,
complexity.
that was going to be my next thing. Like, if you had a cycler and 1 feet of water and you still say that you got it done in 2 months, that's actually pretty good. Like, that's
Yeah,
excellent.
I mean, thanks to the awesome community because everyone kind of pitched in. So we were like, still going despite everything that was setting us back.
Yeah. Yeah, 2 months is actually pretty great to build. Like, you guys have gone through a bunch of prototypes by the looks of it, right? And like, zeolite has been tough to source, and the cyclone and everything. So I guess 2 months is it has to be some kind of record somewhere.
Yeah, usually something like this, an oxygen concentrator or any medical device would take much, much, much longer if we followed a closed loop system or were like
Yeah.
hiding what we're doing and doing it. But like doing it thanks to the community and in an open manner, like Anool was
Yeah.
mentioning, really, really accelerates the process of creation, ideation, and building.
Yeah. I can imagine. Are you guys still having like weekly meetings that are open for people to join in? And like, what's if someone wants to get involved? Like, what's the best way to get involved? So, do
So
they
we
join
have
your
been having
Telegram? Like,
they can join the Telegram group, and we had been having them very up till recently. Right now, we've slowed down a little bit because we're working on the uh, certification, and all of us have been busy with our time on these things. But hopefully soon. What do you say, Anul?
Yeah, pretty much. Like I said, I've been busy doing stuff like finishing off the documentation. That has been quite an effort.
right.
Talking to the certification lab. So action on the Telegram group has been a bit slow, but that's the best way to get in touch. We have a lot of other ways of interacting. For example, of course, there's a GitHub page. I also set up a project page on hackaday.io. So that's another way to be in touch with. But at the end of the day, the GitHub is the main central point of the whole project.
Correct. Right.
And all communications, Telegram, essentially.
Right. Right. Yeah. So the
And
project
the
documentation
links
and
are
everything is on
available on
GitHub.
the GitHub repo or somewhere else, I guess, for the
Yeah. Yeah.
Telegram group.
Yeah, I've shared the link to the keto page and keto.org page, and I've also shared a link to
Yeah,
the GitHub page. And Makers Asylum's website is, as always, pretty well documented. I'm going to post a link for that as well.
yeah,
But yeah, like these guys, like you guys have been pretty busy in the last 18 months, I guess, and like this is looking pretty good. So I guess like all the best for you guys.
Thank
Hopefully
you.
we'll have another of your streams when you are closer to getting this out with the certification and stuff.
Yeah,
But
that'll be a big thing for us.
yeah, like yeah, this was a great thing because I knew about concentrators, but I had absolutely no idea about any of the workings of it and how hard it is to make. But hopefully with your work it's going to be a lot simpler to actually
Yeah, I mean,
think about making one.
none of us knew anything much about concentrators, really, when we started.
Yeah.
And Anul has a famous video over there of how oxygen concentrators are not rocket science. And now I think he can proudly say that it's not anymore.
After we made that, we thought we should make another one which is oxygen concentrators are rocket science because turns out it is both ways, really. It's easy, but it's tough.
No, but
Yeah. And
I mean, I think not just us over here at Makers Asylum, but I think the entire community needs to like take their hats down and like bow down to Anol over here, because
Thank you.
if it wasn't for the resilience of this man, it would be completely impossible to build something like this in such a short time. I think really need to say that personally, I've learned so much, but at the same time, I think the entire community owes you one and all.
Thank you.
Yeah. Yeah. And like the times that we are living in and the importance of this project and the whole initiative around it is also such it's pure, right? Like there's it's so important, and like putting together all that sweat in those 2 months, I'm pretty sure that must have been tough for you guys.
Absolutely.
So yeah, it's pretty awesome.
Well, thanks for having us, Anuj. It's been great. I mean, I love being part of the community. So
Yes, and we
good,
love having you here because yeah, I mean, like where else are we going to find all of these things? So thanks a lot, Vaibhav. Thanks a lot, Anul, for sparing your hour on a Saturday.
also,
But this is awesome, and thanks, Gopachev. I'm not sure if he can hear us, but good luck with his fork of this open source project. Yeah, so good luck with that as well, and hopefully we are able to
And his
follow that up.
jetpacks. I'm more interested for that.
Yeah,
Yes. Great. Thank you so much. Good day.
have
Bye.
a nice rest of the weekend, guys. See you around.
thanks a lot. Bye bye. Thanks
Bye.
everyone for
Thank you.
joining in.